It's a hard knock life for us. We're taking calculus. Instead of slacking, we derive. Instead of sleeping, we will thrive. It's a hard knock life. Looking for limits, go like this to find out if it exists. From the left and from the right, there's three limits all inside. It's a hard knock life. Plug in f of x with h to find your limit. Use h to difference from points A to B. And if you feel like you want to throw the towel in, don't forget to make h small as it can be. As h approaches 0, you'll get closer. A few more steps and you're really almost there. Take rise over line to find the slope of a curve at a tangent point that's smaller than a hair. It's a hard knock life.
Okay, so we're going to try to apply limits to derivatives now, and here's a real example. So for this question, we're going to let f of x is equal to 1 over x. So for the first step, we're going to want to find the slope of the curve at point A. And as you can see here, point A, we're going to want to find a tangent line there, which is going to be equal to our slope at point A. So here's the formula we're going to use in order to find the slope, or the formula to find the slope at point A. And that is, as a limit approaches 0, f of a plus h minus f of a, and we put all of that over h. Now we're going to plug in f of x again, which is of course 1 over x. And we're going to plug in a plus h and a into that value, and we're going to end up getting 1 over a plus h minus 1 over a all over h. Now we're going to simplify that down until we get our final formula, which is going to be negative 1 over a squared. Awesome, so now that we have that, we're going to want to plug in the original slope that we were given in our equation. So in these kind of questions, you're pretty much always going to have to set it equal to some kind of slope. And in this case, the slope is equal to negative 1/4. And it's asking at which point A does the slope equal to negative 1/4. So we're going to set negative 1 over a squared equal to negative 1/4. And in the end, you're going to get A is equal to plus or minus 2.
Yo, we've made it to the junction. Find the area of the function. Calculate region under a curve. First we find the endpoint, keep it up the nerve. On the other side is where you put them down. Go from A to B, matter to lights down. Integrate to the entire nation. Flat curve, stress, function, feeling integration.
Come on, come on.
Feel the integration.
Mathematical equations are old news. Many try to learn them, end up confused. And the goal is the antiderivative, getting creative, function of how to live. X to the n plus 1 of that. Anti-B minus anti-A, yeah. Making up integration or occupation, so you feel the integration.
Come on. Feel it.
So now that Marky Mark has explained to us what an integral is, let's try an example. So for this question, our integral is going to be an integral of from 0 to 1, which are going to be our a and b endpoints, and our function is going to be x squared plus 1, and please do not forget your dx, it's very crucial. So we're going to start by finding the antiderivative of our function, and you do that by doing the exponent plus 1 and dividing that first variable by that exponent. And next, of course, the antiderivative of 1 is going to be x. You can always double check by, of course, finding the derivative of your antiderivative to make sure that you're correct. Now we're going to get that antiderivative, which is 1/3 x cubed plus x. Set that from 0 to 1, and plug in 1 to the antiderivative, and subtract that by the antiderivative with 0 as your x. After you subtract all of it out, you're going to get 1/3 plus 1 minus 0, which is going to give you 4/3. But let's see what 4/3 actually represents. So we can do this by visualizing it by graphing the original function, x squared plus 1, onto a graph. And if we graph it, we're going to be getting a nice parabola. Now, if we locate our endpoints a to b, which are 0 to 1, we're going to see that this integral really represents the distance, or the distance between 0 to 1, and the area under the curve from 0 to 1. So what the integral finds is actually the area under the curve from the two endpoints that you were originally given.